Edexcel Core Pure Complex Number 6 Exponential Form, using the exponential forms of sine theta and cos theta. In a previous video we have seen that cos theta can be written as a half e to the I theta plus e to the minus I theta, and sine theta can be written as 1 over 2i e to the I theta minus e to the minus I theta. Don't forget that e to the I theta is the exponential form of our complex number z. We've previously shown that z, either written in this modulus argument form, is equivalent to this exponential form, and that z to the minus 1 is equivalent to this exponential form. If we look at the case where r is 1, then these become z equals e to the I theta, and z to minus 1 is e to the minus I theta. So if we added these together, we can see that they would add together to do 2 cos theta, and if we subtracted them we get 2i sine theta. So generalizing these two results, we can now say that 2 cos n theta is z to the n plus z to the minus n, and 2i sine n theta is z to the n minus z to the minus n. And it's well worth just double checking and walking through those results for yourselves. So now we can write cos theta to the power n or sine theta to the power n in terms of multiple angles, cos k thetas or sine k thetas. And one of the important things to remember is that by doing this we can make integration much easier to perform. So now the first thing we ought to do is to express sine theta to the power 4 in terms of multiple angles, and in doing so it will allow us to make this integral much easier to complete. So starting off with sine theta to the power 4, I can now write that using our previous definition of sine theta as z minus z to the minus 1 over 2i to the power 4. I'm just going to take out that 1 over 2i to the power 4 as a common factor, and now expanding this using a full binomial expansion, I will get z to the 4 plus 4z cubed minus z to the minus 1 plus 6z squared minus z to the minus 1 squared, 4z minus z to the minus 1 cubed, and finally minus z to the minus 1 to the power 4. So now simplifying this problem, we've clearly got a 1 over 16 there, z to the 4 there. The next term, notice the minus sign, so this becomes a minus 4z squared using laws of indices. Then we get a plus, and these terms will cancel out to leave just the 6. And then the next term is minus 4z to the minus 2, and finally there's a plus z to the minus 4. What we're going to do now, we're going to leave the 6, the middle term, but we're going to pair up the first term with the last term and the second term with the penultimate term. And in doing so, we can rewrite this as a 16th of z to the 4 plus z to the minus 4 minus 4z to the 2 plus z to the minus 2, and then we'll leave the 6 separately. And now what I'm going to do is I'm going to rewrite this 16 as 8 times 2, and I'm going to bring the 2 into this bracket. So this would become 1 over 8 z to the 4 plus z to the minus 4 over 2 minus 4 z squared plus z to the minus 2 over 2, and of course there'll be a 6 over 2 at the end. So now we've discovered that sine theta to the power 4 can be written as an eighth, open the bracket. This first fraction is our definition of cos 4 theta. This next bracket is our definition of cos 2 theta, and of course there's a plus 3 at the end. So we have just written sine theta to the power 4 in terms of multiple angles cos 4 theta and cos 2 theta. Now if we look at the integral that we've been asked to do, so instead of doing sine theta to the power 4 as our integral, we just need to integrate this expression here to get 1 over 32 sine 4 theta minus a quarter sine 2 theta plus 3/8 of theta plus a constant of integration. So the integral was much easier to do, having rewritten sine theta to the power 4 in terms of multiple angles. We would use a similar process if it was cos theta to the power 4. So the things to remember here are your definition of 2i sine theta and the general definition of 2i sine n theta, and likewise for 2 cos theta and 2 cos n theta. So you write sine theta in terms of its definition, and then you can do a full binomial expansion. Once you've done your binomial expansion, you pair up the z to the 4 with the z to the minus 4, the z squared with the z to the minus 2, and if there's an odd term, it should be a number in the middle, which can just sit at the end of the problem. And then by bringing a half back into here, so we rewrote 16 as 8 in order to bring in the half back into here, and then use our definitions of cos 4 theta and cos 2 theta. That allowed this tricky integral to become a much easier integral, which we could do by inspection. In the next video, we're going to be looking at summing series using de Moivre's theorem.